Here I present a proof that the prime factorisation of every natural number is unique up to order. We already showed that every natural number has a prime factor, so now it is my goal to show that this prime factorisation is unique. To begin with, we consider a base case, in this instance 2, which is the smallest prime number. This is clear, 2 is a prime number, and so its prime factorisation is just itself. The product of any other prime numbers would be larger than 2, and so its prime factorisation is unique. Next, we make an assumption as part of our proof by induction. We assume that the statement we are trying to prove is true for all natural numbers up to n. That is, every number, 1, 2, 3, all the way up to n minus 2, n minus 1, n, has a unique prime factorisation. Now we're going to consider the number n plus 1. We know that n plus 1 has a prime factorisation. We've already proved this. So we write the prime factorisation as n plus 1 equals p1 times p2 times p3 times all the way up to ps. And we say that it has another prime factorisation which equals q1 times q2 times all the way up to qt, where pi and qj are prime. By reordering, we state that q1 is less than or equal to q2, which is less than or equal to q3, and so on up to qt, and we state the same for p1 up to ps. This will become useful as we proceed through our proof. Our goal is going to be to show that p1 equals q1, p2 equals q2, all the way up to ps equals qt, and as such we will have shown that the two prime factorizations of n plus 1 are in fact the same, and so the prime factorisation is unique. So, we're now going to consider the case where p1 does not equal q1. So firstly, assume that p1 is less than q1. Now we're going to look at the number we obtain when we have p1 multiplied by, within brackets, p2 times up to ps minus q2 times q3 times all the way up to qt. By expanding the brackets, we arrive at the second line, and we can then arrive at the third line because we know, or we assumed, that p1 times p2 times ps is equal to q1 times q2 times all the way up to qt, which is why we have substituted this in the place of that. We can then factorise this to arrive at the final line, which is q1 minus p1 multiplied by qt times q3 times all the way up to qt. Now we're going to consider that q1 minus p1 has a prime factorisation, which we will denote by r1 multiplied by r2 multiplied by r3 up to ru. Hence, we have that r1 multiplied by r2 multiplied by r3 up to ru times q2 times q3 all the way up to qt is a prime factorisation of p1 outside brackets multiplied by p2 times all the way up to ps subtract qt times all the way up to qt, which was the first line of the computations we did previously, as you can just see here. Now we have that p1 multiplied by this object in the brackets is less than n plus 1, and so by our assumption at the start it must have a unique prime factorisation. p1 is clearly a prime factor. Now, our first case is that p1 is equal to one of the q2 up to qt's. But this is not possible, since we assumed that we were considering the case where p1 is less than q1, and we have ordered our prime factors such that q1 is less than q2, or equal to, is less than or equal to q3, all the way up to qt. So this case, where p1 is equal to one of the q2 up to qt, is not possible. Second case is that P1 is a prime factor of Q1 minus P1, and so is equal to 1 of the R1 up to RU. But this implies that P1 divides Q1, because if P1 is a factor of Q1 minus P1, that means it divides this full number. Obviously P1 divides P1, so P1 must also divide Q1 in order to be a factor of Q1 minus P1. However, this can't happen because Q1 is a prime number, and P1 is greater than 1, but strictly less than Q1. By this logic, we've shown that P1 cannot be less than Q1. We apply the same argument in reverse to show that P1 cannot be greater than Q1. So, this leads us to deduce that P1 must be equal to Q1. Now, P1 equals Q1, and they are both greater than 1. Now we deduce that P2 multiplied by P3 multiplied by all the way up to PS equals Q2 multiplied by all the way up to QT are less than n plus 1. We assumed at the beginning that all numbers that are strictly less than n plus 1 have a unique prime factorisation. Therefore, these two numbers, which are composed of a product of prime numbers, must in fact be composed of the same prime numbers. We deduce that S equals T, that is, each list has the same number of prime numbers in it, and because we wrote the factorizations in increasing order, we can see that P2 equals Q2, P3 will equal Q3, and so on, up to PS equals QT, which is the same as QS. It should now be clear to you that we have shown that the two factorizations of n plus 1 that we stated at the beginning are in fact the same, and so prime factorization is unique. By showing that if all the numbers up to n have a unique prime factorization, this implies that n plus 1 does as well, we have clearly shown that every natural number has a prime factorization and it is unique up to order.